In this video, we're going to look at a strategy for solving limiting reagent type problems. So the first thing we want to do is read the problem and sketch a container to help us clarify what is present. While containers like this are really useful for organizing our work and organizing our thoughts, we've already discussed how using grams or things like that is not going to be really useful. And the first thing we're going to want to do is convert from grams into moles. So do that and then hit play. Hopefully you got the same contents that I did. I simply took the mass, say 3 grams of ethane, and multiplied it by the reciprocal of its molar mass, so 1 mole of ethane is equivalent to 30 grams of ethane. And doing this, you get that there is 1/10 of a mole of ethane present in our container, and the same thing applies to oxygen. Once we know what we have in front of us, we can start making predictions about what kind of reactions can take place. So we know that ethane will burn in oxygen to make carbon dioxide and water. Hit pause and fill in the coefficients using the skills we've developed before. Hopefully you got the same coefficients that I did. Possibly you got double the coefficients and didn't use a fraction. But remember, fractions are okay here because we're not actually talking about molecules, but rather just the ratio. And we know that for every 1 ethane, we're going to use 7.5 oxygens. Really, we're talking about molar quantities. And so numbers like this make a lot of sense. Now that we know what the ratios between the reactants are, it's time to see which one is going to be our limiting reagent, meaning which of these two will finish being consumed first, and therefore there will be none of it left to react with the excess of the other, and therefore the reaction will stop. It is possible, of course, that we have precisely the right amount of both to consume both completely, and we'll find that out as we move forward. The most straightforward way to figure out which one of these is the limiting reagent is to actually go systematically and assume that each of the reactants is potentially the limiting reagent and see how much product would form. So for example, if we assumed that the ethane were the limiting reagent, 0.1 moles of ethane, when it reacts completely, you'll make 2 moles of carbon dioxide for every 1 mole of ethane that is present, and that we got just from our balanced chemical equation, which means we would get 0.2 moles of carbon dioxide. So if ethane is the actual limiting reagent, we would make 0.2 moles of carbon dioxide. Now, without skipping a beat, we're going to right away assume that oxygen is the limiting reagent and do the calculation that way as well. So 0.4 moles of oxygen. If they were to react completely, we would make 2 moles of carbon dioxide for every 7/2 mole of oxygen that is consumed. And as a result, we would make 0.25 moles of carbon dioxide. Now, clearly, both of these can't be the case. In fact, we know that once we've made 0.2 moles of carbon dioxide, all of the ethane has been consumed, which means it must be that the ethane, in fact, is the limiting reagent. For if it wasn't, it would keep being consumed until we made 0.25 moles of CO2. So whichever one of these is the smaller number, that tells us which reactant is limiting reagent. Finishing this problem involves taking the amounts of reactants that we started with and finding out how much is left in the container and how much of the products we form. So we know that the ethane was our limiting reagent, which means we will have 0 moles of ethane that are remaining at the end of the reaction. We also calculated that 0.2 moles of carbon dioxide would form. To figure out how much water forms, we can simply use the stoichiometric ratio that we had in the balanced chemical equation, and we know that 3 moles of water form for every 2 moles of carbon dioxide that form, which means that we're going to have 0.3 moles of water that form at the same time. So now all that's left is to figure out how much of our excess reagent, oxygen, is remaining. Similarly, we start with the amount of carbon dioxide that forms, and we recall that for every 2 moles of carbon dioxide that form, we must have used 7/2 moles of oxygen, which means we've used 0.35 moles of oxygen gas. And since we started with 0.4 moles and we've consumed 0.35, we have 0.05 moles of oxygen remaining, and we add that to our container. And just like that, we can now answer any question that we want about the contents of this container, and therefore anything about this problem.